Okay, we're going to talk about the falling object model, and I'm going to talk about different ways that you can solve this. I'm going to concentrate a little bit more, though, on solving it by factoring, but you can use all kinds of methods to help use this depending on what's going on. It's important to realize what's happening when you talk about something going in the air. Falling object means exactly what it's saying. Something goes up, something comes down. When that happens, we can see that we've got an upside down parabola. And usually what's going on is that we're going to be tracking time and height. That's usually what's going on and what's happening with this particular types of problems. Now, the parabola can shift. We can have an initial height where we're standing on top of something and we're dropping, let's say, throwing water balloons at somebody down below. We're obviously going to be starting out a little bit higher. But there are times that, let's say, you're kicking a hacky sack and you'd be starting the hacky sack from the ground, or a soccer ball from the ground, and it would be going up and coming down. So we can see that even though that we can have different places where this could be occurring, different things will be happening, and we can see how the slide affects us. One of the things to note is that when it doesn't start on zero, or when it does, even when it starts on zero and anywhere to the left, we're going to be getting an extra solution that is not going to make sense in the real world, because we know that the real world exists in quadrant 1. That's where it is, right here in quadrant 1. Only the answers that are in this quadrant are in the real world, and that ones that we use in time. And if you are hard pressed to think about that, let's apply time in the real world. Can you have negative time? Do we do things in negative seconds? No, we don't. How about negative height? Same thing. We do talk about under the water and degrees below and things like that, but never really in height from the ground up. We don't really get into negative height. So we're going to talk about real world when we're talking falling object. So let me give you a look at what a typical equation looks like. They'll always start out with an H, and that H represents the level where you want it to stop. Usually we're talking about when it hits the ground. So if we're talking about when it hits the ground, we're obviously going to put a 0 there. That 0 is going to help us to be able to either factor it or do all kinds of things with it. So think about that. If it's going to stop on the ground, you'd put 0. If you wanted to stop 5 feet above the ground, you'd put a 5 there, depending on what's going on. The T here, and I put a T for time because we usually take the time in seconds, but I put the T there to think about time, but sometimes we see an X there. We might see another variable there, but that variable that we're using is going to represent time. And I have S sitting here, and that would really be our constant. Our constant is going to tell us what our initial height is. So if we were starting from the ground, this would be 0. If we're starting on top of a building because we're throwing water balloons, we'd be 36 feet up, or however high that number would be here. So that would be our shift up and down the y-axis. You'll notice that there's no B term in this particular one, but there can be. It's just there isn't one in this particular one. And again, remember, we're talking about a quadratic. So let's just take a look at one problem, and we'll kind of model this a little bit. So it says the height in feet of a diver above the water can be modeled by h of t equals negative 16 t squared plus 8t plus 8, where t is time in seconds after the diver jumps off a platform. Find the time it takes for the diver to reach the water. So what we're looking for is we're looking for this diver. He's going to jump up and land in the water. We can use our equation of h of t equals negative 16t squared plus 8t plus 8. And if we're thinking about this, remember, here's our coordinate plane, right? He's starting a little bit higher than we thought. So we're going to end up with a solution out here that we may not necessarily use because it's negative time. So we've got to keep that in mind, what's going on. Now, there are many ways that we can solve this. We can solve it by graphing, by finding the axis of symmetry. And then after we find the axis of symmetry, we can find out how far away we get the vertex, and then pick another point and mirror all the way down till we get to a 0. Now we could do that. That's lengthy and it can cause mistakes. Another way, which is really good to use, is if we want to, is to do it by factoring, which is the way I'm going to approach this. So since we want the time it takes for the diver to reach the water, that height's going to be 0. And what we're going to do is take a look at this side and say, what's our greatest common factor? Hopefully we realize it's 8, and I want to factor out a negative 8 because I don't like that first term to be negative. So that's going to leave behind 2t squared minus t minus 1. If we multiply that, will get us back to where we were. So then I'm going to use the diamond method just like we did before, to factor this trinomial. So -1 times 2 would be -2 on the top, and -1 would be on the bottom. I need a negative number and a positive number to multiply together to get -2, add together to get +1. That would be -2 and +1. So I'm going to rewrite that trinomial, and that's going to be 2t squared minus 2t plus t minus 1. Now what I'm going to do is I'm going to cut it in half, and I'm going to factor out the left side. So again, 0 equals -8 times, and I'm going to pull out a 2t, because that's the greatest common factor there, leaving behind t minus 1. Write that binomial down on the other side, and I would multiply t minus 1 times +1 to get t minus 1. Again, I take a look at this, and I see the greatest common factor is t minus 1, so I'm going to pull that out. So 0 equals -8 times t minus 1, and leaving behind 2t plus 1. So now that I have it fully factored, I'm going to extend this down a little bit. Now that I have it fully factored, I've got to take a look at what's happening. -8 times something is going to give me 0. Well, I know it's not -8. That's not going to work out. So I'm going to take each of these factors, and I'm going to set them equal to 0. So I have t minus 1 equals 0, and 2t plus 1 equals 0. I'll solve the one on the right. -1 to both sides, 2t equals -1. I divide both sides by 2, and I have an answer of t equals -1/2. This other one, I would add 1 to both sides, and I would get t equals 1. So here are my two solutions, 1 and -1/2. Now remember, we looked at our picture up here, and if we remember correctly, we knew we were going to get two solutions, but we know that one of them is going to be extraneous. Extraneous means that yes, it does solve the problem, but it doesn't solve the real world problem. So we do have an extraneous solution here. Our extraneous solution is this t equals -1/2, because we can't have -1/2 seconds. So our answer to our problem is that it takes 1 second for this to occur. Now, for some people who are a little bit skeptical, they're thinking, how can jumping off a board land in 1 second? Go back to the problem and realize what's happening. Remember, this 8 tells us that they're only 8 feet off the ground. They're not very high. So yeah, it takes about 1 second before you would hit the ground if you were jumping off of something, or if you were jumping off a platform into a water that's only 8 feet off the ground, within 1 second, you'd be in the water. So hopefully this helps explain how to use the falling object model a little bit better.